So in this section, we're going to take a look at some of the properties, some of the characteristics of the condensed phases, and these are going to be dictated by our intermolecular forces. And remember, we talked about these in some of the earlier sections. These are attractive forces that hold particles together in the condensed phases. So if you remember, some of the intermolecular forces that we talked about were things like we had our dispersion forces, which were the weakest. We had our dipole-dipole attractions, which you find between polar molecules. We also found hydrogen bonding. We had special criteria that need to be in place for that to exist. We also saw ion dipole attractions as well. Okay, so we're going to be invoking all of these uh, intermolecular forces to explain some of the characteristics of the condensed phases. So as a quick reminder, when we talk about intermolecular forces, the name actually means molecules, but we use them to refer to the attractive forces that hold any particles together. So these could be, they could be molecules, they could be atoms, individual atoms, or they could be ions. So even though we use the term intermolecular, we're really looking here at just particles in general and how they keep the condensed phases together. So a quick reminder also with our condensed phases and states of matter in general, we talked about three of these. So we talked about liquids, we'll talk about gases, liquids and solids. Okay, we talked about gases in some appreciable extent in the previous section. And if you remember from the kinetic molecular theory, for our gases, the intermolecular forces, IMFs, okay, really don't play a significant role between the particles of a gas, so we can say are negligible. And this is according to the kinetic molecular theory. So our intermolecular forces of attraction then will become more relevant when we start looking at the liquids and solids, and these are going to be the condensed phases, right? This is where the particles are a lot closer together. They're very close together, especially when you compare them to the gas phase, whether in the gas phase they're more spread out, a lot of empty space between them. That is not the case with the liquids and the solids, so we refer to them as the condensed phases. So the strength of the intermolecular force, or the magnitude, that just means the strength, together with the type, and they kind of go hand in hand because different intermolecular forces have different strengths. They will determine whether the particles that make up a solid are either going to be the gas, liquid, or solid phase. All right, so in a gas, the particles are spread out, a lot of empty space between them. In a liquid, the particles are close together, but the particles can slide, so there is freedom of motion. Of the liquid particles, right? They can slide past each other. Whereas in the solid phase, the particles really don't have a lot of motion. The particles you can think of as being locked in place. Okay, and then again, the solids and the liquids, these are going to be our condensed phases that we're going to be talking about. So what are some of these properties that we're going to be focusing on? Well, there are several of them. We're going to take a look at surface tension, which is going to apply to our liquid phase. We're also going to be looking at viscosity, also for the liquid phase. Then we're also going to be looking at vapor pressure, which applies to both the liquid and the solid. So I'll just do liquid and the solid phase. And then we're also going to be looking at phase transition temperatures, which then will obviously apply to all three phases. Okay, so these are what we're going to be focusing on in this section of this part of the course. So the intermolecular forces applied to our condensed phases, solids and liquids, are going to be a focus here. So our first property that we're going to take a look at is something called a surface tension. And you can think of the surface tension as a measure of the elastic force in the surface of a liquid. And it's referred to as the amount of energy that's required that you need to stretch or to increase the surface of a liquid by a unit area. And that unit area is typically expressed in, let's say, at 1 square centimeter. Okay, so again, surface tension here is going to be the measurement of the energy needed to stretch the surface of a liquid by a certain amount. So if you have a beaker here, these are water molecules. Okay, and if you remember, okay, H2O, our molecular shape, it is bent, and then H2O has a net dipole. The oxygen is more slightly negative than the H's. And then compared to if we had a neighboring water molecule close by, okay, the ingredients are in place for hydrogen bonding to exist between the H on one water molecule and the O on a neighboring one, right? So this is a hydrogen bond that exists here, our intermolecular force of attraction. And it is a strong intermolecular force of attraction. So when you have these neighboring water molecules around a particular water molecule, if you think of a water molecule down here in the middle, it is actually being attracted to everything else around it, to the left, to the right, to the top, to the bottom. One at the surface, though, is being pulled to the left, or it's being attracted to the left, to the right, to the bottom, and also to the sides. But there is no net pull pulling this upwards. And the net effect of that then is a net pull inward on the molecules at the surface, and that causes the surface of a liquid, in this case water, to tighten kind of like an elastic film. So there is no pull outwards at the surface, right? Because there aren't any water molecules above it. So this causes a tightening of these surface water molecules over here, kind of like an elastic film. And what this results then is there are several ramifications of this. It causes, for example, if you wash a car and then it rains, you typically see that the water kind of beads up. The other effect of this, and you probably have seen this as well, is that sometimes you can actually see bugs like maybe spiders and stuff are able to actually can walk across the water. Okay, and that is as a result of the very high surface tension of H2O. It takes a lot of energy to break that surface tension to increase the surface by a certain area. So the general trend here that we're going to see is that the stronger the intermolecular force of attraction, right, the higher the surface tension is. And in the case of H2O, where we do have that very strong hydrogen bond as our intermolecular force, right, H2O has a very high surface tension as a result. Okay, and you can even test this on your own if you have a glass of water at home. You can carefully place let's say something like a paper clip on the surface, and it doesn't sink immediately because it's able to actually be held in place by the very strong surface tension, high surface tension of the liquid itself. So another effect of the high surface tension of water is something known as capillary action, which is the movement of a liquid, in this case, water is our example, up a narrow tube. And you can think of if you've ever had your blood drawn, in some cases, depending on the technique that they use a very, very thin, they can use a very, very thin tube called a capillary tube. And if you just place it at the surface, let's see if where there's blood, for example, the blood actually gets sucked into the tube due to the surface tension of water because the water molecules actually try to constrict and be attracted to each other and actually pulls one another. They pull one another actually up into the tube. And that's known as capillary action. That's a direct result of the high surface tension of H2O. There are a couple other types of forces that can also bring about capillary action, and they also result in what you've seen before, which is the meniscus shape that we associate with water in a cylindrical tube. And these types of forces are known as cohesion or cohesive forces. And then we also have adhesion or adhesive forces. Okay, and the difference between them is simply uh, what are the forces attracting? What two things are the forces being related to each other? So in a cohesive force, it's the attraction, or cohesion is the attraction between like molecules. Okay, so in the case of our example with water, this would be the attraction between the H2O molecules. Now let's say the water was in a graduated cylinder, for example, like this example down here. Well, then we can contrast that with an adhesive force or adhesion, which is the attraction between unlike molecules. And this would be the attraction then between the water, and the only other thing that is not water in a graduated cylinder is the actual graduated cylinder itself. So it would be between the water and the walls of the graduated cylinder. And what you actually see in the case of water, this is our H2O over here on the left side, is that the adhesive forces, okay, the attraction between the water and the walls of the graduated cylinder is actually greater than the attraction between the water molecules themselves. As a result, what you'll actually see is the sides where the water is in contact with the glass, the inner glass, the attraction there is actually stronger. So the water actually climbs the glass more than it is being attracted to the other water molecules. As a result, you have a very characteristic meniscus, right, that looks like this. So the meniscus shape here, right, is very distinctive. And that's called a concave shape. We read the bottom of the meniscus when we have a water meniscus. In the case of, I think this is mercury here on the right side. We don't use mercury in the lab, for instance. We actually don't use mercury thermometers anymore. But if you did, what you'd actually see is that the meniscus for mercury is the opposite. It actually has a convex meniscus. It actually has an opposite smiley face. And again, we'd read the top of the meniscus in this case. And the reason for the difference in shape is because the cohesive forces between the mercury atoms, okay, are stronger than the adhesive forces between the mercury and the walls of the graduated cylinder. And as a result, that shape, that convex shape, becomes adopted in mercury compared to the concave shape that we see in a typical water sample when it's in a thin tube like a graduated cylinder.